Yes, we are live already. Hi, everyone, and welcome to day two, the security day of Cloudflare Week. In this session, we will meet Alec and João, who are going to demystify the second factor in authentication and navigate the intricacies of infrastructure security in serverland. I'm Joanna, I'm part of the Landing.Jobs team, and I will be your host for today. As we are waiting for everyone to join, I hope you are all well seated, well resting, hearing us properly, and ready for the next hour. For those of you who don't know yet, Cloudflare is on a mission to help build a better internet. Cloudflare protects and accelerates any internet application online without adding hardware, installing software, or changing a line of code. Internet properties powered by Cloudflare have all traffic routed through its intelligent global network, which gets smarter with each new site added. As a result, they see significant improvement in performance and a decrease in spam and other attacks. Today, we have here with us Alec and João. Alec is an infrastructure security engineering manager that is going to demystify the second factor. Authentication is core to everything we do online, so in this talk, we will address why a simple username and password are not enough in knowing who is behind an action, as well as addressing common forms of multi-factor authentication and their failings. We also have João, infrastructure security at Cloudflare, and is working on boot security, TPMs, and disk encryption. João enjoys reading about everything security related, with a special emphasis on cryptography. João is here to navigate the intricacies of infrastructure security in serverland by taking a look into how protecting servers differs from protecting end-user machines from an infrastructure security point of view. We are also going to talk about trusted platform modules, TPMs, what they are, and how can they be leveraged to address some security requirements that exist on large-scale server deployments. For the ones that just joined, welcome. I'm Joanna, part of the Landing.Jobs team, and I will be your host for today. We are here with Alec and João from Cloudflare, and we are about to start the two presentations. After each talk, we will have a Q&A moment, so if you have any questions throughout the sessions, please feel free to do the questions in the Ask a Question button you find in the bottom right of Crowdcast, and we'll answer them at the end of each session. Also, during the presentations, feel free to leave some comments on the chat if you want. We'll keep an eye on it. And if for some reason you stop hearing us, seeing us, wherever, if something's not working, also let us know in the chat and we'll try to solve it as soon as possible. Yeah, I think that's it. Alec, thank you so much for being here with us today. The stage is now yours.
Thanks, Joanna. I'm going to go ahead and share my screen. But while I'm doing that, my name is Alec, and I've been at Cloudflare for about 3 years, just a little over 3 years now. And I moved to Portugal when we opened up our Lisbon office back in August of 2019. It's been an interesting time to be working and living in a new country, especially remote with everyone, but I think we've done a great job, even though none of us have been to the actual Cloudflare office at this point. Hopefully we'll get to do that soon. Let's see, hopefully, it looks like my screen is being shared. Cool. As mentioned, João and I are on the infrastructure security engineering team here at Cloudflare. And so we spend a lot of time digging into things at the Linux kernel layer and below, which is a really interesting thing at Cloudflare because we run hardware all over the place. And so we're not outsourcing things like firmware security and TPMs and all of that really kind of cool infrastructure stuff to another company. We're taking care of it all ourselves. But instead of just talking about that for 2 talks today, I thought I would go up the stack a little bit and just talk about authentication at a high level. Authentication is really important to so many things at Cloudflare, and particularly as the world has started shifting to remote work, we have employees who are authenticating from all over the world, no longer from offices, and oftentimes with lots of different setups at home. So we've lost a lot of uniformity. And while we're talking about authentication, I think it's also important to note that this is probably the most common aspect of anything that's attacked from a security perspective. we see attacks on authentication all day, every day, on both Cloudflare infrastructure, Cloudflare services, and all of our customer services as well. And so making sure that we are able to secure our authentication is crucial to securing everything else up and down the stack from there. And so to start, I think we can look at just a single factor authentication. We have a user who enters credentials into an application, which verifies the credentials. And if the credentials are correct, then you're authenticated and you're able to move on. Now, obviously, there are a lot of like potential pitfalls with this, and I'll get into some of those in a minute. But this is the most like basic form of authentication. Most commonly, just going to be a username and a password. A pretty long while ago, it was basically determined that the single factor methods of authenticating someone is no longer really enough to really know if it's who you want to actually be taking actions inside of something. And so we have multi-factor authentication. There are basically 5 core ways to add a factor to authenticating someone. Five core ways to just know if someone is who you expect them to be. The first is something you know. Most commonly is going to be a password. Something you do, which I'll get into some examples of those in a minute. Something you are, something somewhere you are, or something you have. Going through those in order, something you know, like I said, is most commonly going to be a password or a passphrase. There's a lot of issues with just this single type of authentication, but it is the most commonly used, and it is an important aspect of building a strong set of authentication mechanisms. Passwords have a few common weaknesses. This is not an exclusive list, but these are some of the more commonly seen problems. Default credentials, we see this time and time again. It's always in the news, someone not changing the admin username and password on something. This also can exist in a way where if someone gets a password reset, it'll often be reset to a default password. And if a user forgets to change it, then it becomes easy for someone to guess. As computing power has grown over time, we also see brute force attacks, and we see smarter and smarter brute force attacks. A brute force attack is really just guessing every possible combination of for a password. And some of the smarter brute forcing mechanisms at this point do things like guessing patterns. So if you've ever worked at a company that, say, requires you change your password once a month, a very common technique for users who don't want to have to remember a new password is to just append the month to the end of that password. It's like password January, password February, password March. And there's a lot of different kind of patterns that fall with this. If you have to change your password quarterly, sometimes you'll see spring, summer, fall. And if it's annually, you'll see the year put at the end of these. And then the third most common weakness with passwords is password reuse. And this is, again, comes down to users needing to remember these passwords. And it's easier to just remember one password and use it in multiple locations instead of trying to remember one for each service. This is where password managers and things like that becomes very, very useful. The second kind of authentication factor that we can talk about is something you do. In a lot of ways, these are very similar to passwords, but instead of just being a string of text, it's something that you can replicate that acts the same way as a password. The most common examples of these are Android swipe unlock and the Windows picture unlock. The Windows picture unlock is really easy to relate to a password. It's something that you know. And the swipe unlock, really, you just have to know the pattern as well. And so the same type of issues that you see with passwords tend to also fall into these two examples of something you do, in most categories of something you do. A lot of people will often group something you do and something you know into a single group of authentication factors. The third factor that was on the list is somewhere you are. And this is not a bad factor, especially compared to the previous two. However, it does become pretty difficult to implement. The most common ways that you'll see somewhere you are being implemented as an authentication factor is with something like IP allow listing, where only a very specific IP address is allowed to authenticate to a service. The issue you run into there is in today's mobile world, especially with everyone working remote, and a lot of home ISPs not granting static IP addresses, it's very difficult to have a set of allow listed IP addresses that can authenticate somewhere. And so it's pretty uncommon to see a lot of services using IP allow listing, even though it is one of the most common somewhere you are mechanisms. The second is geo IP. You can use something like IP address locations to determine if it should be somewhere that a user is authenticating from. An example is we don't expect employees based out of our Lisbon office to be authenticating from somewhere like Madagascar. And so we can use something like the location that a person is authenticating from to determine whether or not they should be allowed to authenticate. This, however, is fairly easy to defeat if you just know what types or what locations are allowed because of things like VPNs. And so it's not the strongest of ways to really authenticate somebody unless you're using a strict IP allow list. Something you are. So this is a pretty strong way of authenticating a person. Something you are tends to be biometrics. So things like your fingerprint, your retina or eyeball scan, voice recognition or facial recognition. The big issue with these biometric or something you are types of authentication is it becomes very difficult to change them, if not impossible. Changing your retina is, for all intents and purposes, not something you can do. And even though things like your fingerprint and your voice might modulate a little bit, you can't change them enough to drastically change how these biometric readings actually work. And so as compared to passwords, which you can change on a whim and regularly or as frequently as you want, the something you are factors are very static. And if it ever leaks or becomes no longer unique for some reason, then there's no way to fix it and make it so that it still authenticates only you. And we've seen issues with things like the fingerprint readers on cell phones being mimicked with, say, like a gummy bear and a picture, or Face ID has been broken with intricate masks that people have worn. And so once one of these is broken, it's almost impossible to recover from it, which is the big problem with the something you are and why it hasn't really taken off too much beyond things like cell phones. So finally, getting to the end of that list is something you have. And this is the most common type of second factor authentication. And the reason for that is because of all the kind of pitfalls that I mentioned earlier, talking about the other types of multiple factors for authentication. So something you have is easily changed. And it also adds a little bit of difficulty to authenticating for a malicious attacker without having the problems like biometric auth does or location-based auth does. The three most common something you haves are implemented through SMS or text messages, TOTP, which is often something like Google Authenticator, or an actual physical device that you have in your possession. And the two types of physical devices you see the most often are actually either just a physical device that implements TOTP the same way that Google Authenticator would, or a U2F or WebAuthn device, the most common brand of which you tend to see is a YubiKey. There's also Google Titan keys and FETAN keys and a lot of other things that implement the underlying protocols of either U2F or WebAuthn. Starting at the top of these, SMS is probably the least secure of these something you have factors. The last time we had a security Landing.Jobs presentation, I went into depth of the anatomy of an SMS attack, specifically from the perspective of cloning a user's SIM card, which allows you to then receive the text messages intended for that particular person, including things like an SMS authentication code. This type of attack is fairly common, and we see it regularly. We've had multiple Cloudflare employees be targeted this way. And because of that, we no longer use SMS authentication at Cloudflare for anything. It's particularly in the United States, very easy to clone somebody's SIM card. Easier for some cell providers than others, but it's overall just not a safe way for authentication. But even beyond the SIM cloning, SMS is kind of vulnerable to some of the same things as TOTP. But before going into that, just a quick overview of how the SMS as a second factor works. A user will enter their credentials to an application, which verifies those credentials, generates a code, and sends it off via SMS to the user's mobile device. The user will receive that SMS and enter that one-time code into the application. And the application verifies it and then authenticates the user. Now, the other thing to kind of point out here is I've added blue lines to these diagrams to show where SMS is vulnerable the same way as TOTP. And it's really just the interactions between users and the application. And so you'll see that line as a different color on these diagrams. Now, I mentioned SMS is vulnerable in the same way that TOTP is, and just a quick overview of TOTP before going into that vulnerability. TOTP is a mechanism where a generated secret is shared between usually a mobile device, sometimes, like I mentioned, a physical device. That secret is shared between the two, the mobile device and the application. And then when someone goes to authenticate, that secret is used to generate a one-time code. And that code is entered alongside the credentials into the application, which verifies the credentials and the one-time code, and then authenticates a user. And so there's this common interaction here where users are taking one-time codes, either generated and sent by SMS or generated by an application in a TOTP format, and entering them alongside passwords to an application. These credentials and one-time codes are vulnerable to man-in-the-middle attacks, often perpetrated by phishing. EvilGenX is a kind of proof of concept piece of software that allows you to set up a reverse proxy that would sit in between the user and an application. It doesn't have to be EvilGenX. It could be anything kind of performing the same tasks. But this is a ready-made example. And basically what happens here is a phished user would see a valid SSL or TLS connection to the EvilGenX server, which then pretends to be a login page and will accept your username and password and one-time code, and then just forwards it to the actual intended website and acts as pretty much just a proxy in the middle of this connection. So it looks like everything goes okay, but your session is now running through this attacking server. The reason this works is because those one-time codes are not tied to anything specific. The codes can be used by anyone, anywhere, because it's just a number either sent via SMS or generated by TOTP. And so this is where the kind of last device that I had talked about being a U2F or WebAuthn device comes in. And this is kind of what we do at Cloudflare for our multi-factor authentication. We have phased out TOTP almost entirely. There are a couple examples of TOTP that remain, but we're actively making sure that everything uses U2F when possible. And if something doesn't support U2F, we use some of the Cloudflare products like Cloudflare Access to sit in front of those services, so that even though the application doesn't support U2F, we have authentication with U2F or WebAuthn put in front of it, so that everything requires these physical tokens. And the way U2F works is it can be a little complicated. So instead of having a ton of diagrams, I wanted to just focus on this one. And basically what happens is during a login request, the application or server will generate a challenge, which is sent back to the user's device. And that challenge gets signed by a private key on the physical device. And in that signature and challenge, it also includes the URL of the website attempting or asking for the credentials. So if you end up at evilgenex.com, the signed token will only be valid for evilgenex.com, and it can't be forwarded to the actual intended website, so something like gmail.com. That signed challenge is sent back to the server, which will then verify it against the user's public key. They'll also make sure that it's the expected domain name inside that signed payload. And if everything matches, then the user is allowed to log in. So these devices are great for preventing things like phishing attacks from being successful, and it basically knocks them out completely, as long as it's the only form of second factor allowed, and second factor is required. So with that, I think I'm already slightly over the allotted time that I was given, but does anybody have any questions for me?
You are right on time, Alec. Don't worry about that. Actually, we have a question in the chat. As someone moving from service desk system admin to a IT security manager position, in your opinion, what are some of the most sought after certifications in the information security field, and which certifications or courses, trainings would you recommend?
So I think there's quite a few answers to that. And it kind of depends on what direction you want to go in information security. I tend to break up information security into a few categories, application security being one, detection and response being another, and compliance being a third. And those three tend to have really very different, but also very strong certifications. In the application security world, I think some really good training materials are things like the OSCP, which is the Offensive Security Certified Professional. It can be difficult at times. They're not known for being the most accommodating to questions. Their response to questions tends to be try harder, which is not very helpful, but the training materials are great. And I think if you can work through the OSCP lab, you can work through most anything that you would need to do as an application security engineer. On the detection and response side, I'm not as familiar, but SANS, S-A-N-S, tends to have really good material for almost all aspects of security. And then on the compliance side, I actually don't know very much about compliance security at all. I would suspect SANS has some things, but also things like a CISSP would be helpful in that particular realm, I suspect.
Okay, thank you so much. Matthew, please let us know if you are, if the question was answered, if you have any other doubts. For now, we don't have any other questions, but I have a personal question for you, Alec.
Okay.
Since you are working at Cloudflare for 3 years, correct? For 3
Yes.
years, more or less. What is your favorite part of working at Cloudflare?
So I think the coolest part about working at Cloudflare for me is the work we do changes the internet regularly. Sometimes that can be a little scary. I think Joao might attest to the first time he pushed code to production. If it breaks, the internet notices, and they notice very quickly, and so it can be a little nerve-wracking. But at the same time, the other side of that is we have a real impact on the internet with what we do. One of my favorite anecdotal graphs to look at, I can't remember where it is exactly, but there's a graph of things like HTTPS adoption across the internet over time. And so it shows how many websites, what percentage of websites use SSL or TLS. And it's slowly trickling along, growing it's in the low 20%. And then there was the day that Cloudflare decided to give away free HTTPS certificates. And the graph just skyrockets. And then from there, things like Let's Encrypt came around, and it just skyrocketed even more. But we tend to be at the forefront of pushing new things out on the internet, and you can tell how it changes things. Things like HTTP 3, which is not really a fully adopted standard yet, but we support it. Things like I said, SSL or TLS adoption for free. HTTP 2 was also another example of something that we just pushed out and is now almost universal. It'd be weird to not have HTTP 2. And then the other thing about that is there are other places where you can have impact on the whole internet, but there are not a lot of places where you can have impact on the whole internet the way you do at Cloudflare. A lot of these other internet scale, to use a buzzword, companies are 100 or 150,000 people. And at Cloudflare, we're still much closer to 2,000. So the percentage of impact per person is just a lot higher than anywhere else. And we do it all without selling advertisements and invading people's privacy. So I guess that's the three things put together that just don't exist anywhere else. Changing the internet in a meaningful way at a smaller company without selling advertisements.
Great answer, Alec. I understand part of it since I'm not technical, but I'm not from the tech area, but I understand that Cloudflare is doing a great job. We have two questions here. One of them is, what do you think about the great hack of SolarWinds and the ones that came after?
SolarWinds was an interesting one. I think the most interesting part about SolarWinds in my mind was just how widespread it was. And it's kind of a good reminder that at somewhere like Cloudflare, we need to be extra vigilant, because an impact to Cloudflare is an impact to the internet, just like an impact to SolarWinds is an impact to basically the entire Fortune 500. I don't know what percentage SolarWinds actually had as a customer base, but it was a lot. And then governments all over the world. It does come back to Joao and I get to work on crazy things like TPM-based disk encryption and hardware roots of trust for UEFI firmware. But it's a good reminder to not forget about things at the much higher levels. The SolarWinds hack was not someone crafting special UEFI image to go and do crazy things at the kernel level to take over machines inside a data center. It was just a much higher level attack, which is why kind of the same reasoning that I had for talking about authentication instead of Linux K probes. And then what was the second part of that question?
It was, what do you think about this great tech of Torrents and the ones that came after?
Yeah, the ones that came after, I think same thing. Like you can't forget the basics while working on the more intricate aspects of security, because time and time again we see that's how most of these major hacks tend to happen.
Okay, and we have a last question before we give the word to João. If you are not a fully developer-geared IT professional, what would you consider the best way to move into the arena of security?
So I mentioned 3 kind of areas of security earlier. There are more than 3. I think if you're already an IT professional, moving into IT security is a very logical step. Oftentimes, people, just the same way that I think developers who want to move into security tend to, like, a logical step is moving on to an application security team or a development security team. IT security is still arguably one of the most important parts of security. All the SaaS applications and like IAM and just kind of laptop like endpoint security. All these things are super important to keeping an enterprise safe. And I think if you're, like I said, if you're already an IT professional, it should be kind of second nature and just building upon that in the security specific realm.
Okay, perfect. Thank you so much, Alec, for answering the questions and for your presentation. I would kindly ask you to stop sharing your screen. And João, welcome to the stage.
Thank you very much, Joanna. Thank you very much, Alec. Just give me a second
to
share my screen. I believe you can see it now.
Yes, perfect.
That's great. Thank you very much. Good afternoon, everyone. My name is João Lima, and I'm an infrastructure security engineer at Cloudflare. As Alec already described, the team I'm working with helps securing Cloudflare's hardware fleet. We basically live on the hardware-software interface, which is a very interesting place to be working on, if you ask me. And I'm here today to share some predominantly personal thoughts on the differences between securing end-user machines like desktops and servers. So the generation you belong to is probably going to determine if you associate the poorly attempted pun on the talk title with either the gentleman on the left or with the gentleman on the right. Hairstyles and fashion standards aside, it doesn't matter much which song you relate with, as both songs actually talk about the deep affection the subject has with someone or something. I don't really know if that's the case for you, but to an extent, these songs describe how I feel about my computers. They are machines I care about, since much of my daily life depends on them keeping to work properly. But more than them just working properly, I want to be sure the things I do with them and the data I store in them is secure. Because of that, I end up spending a fair amount of time making sure that my system is kept in a secure state, installing updates, maintaining passwords, doing some validation before installing new software, etc. This ends up being a somewhat time-consuming process, and it's adapted to the use I make of my own machines. So as much as I would like to just do the same with the servers we have on Cloudflare's infrastructure, it's not really feasible to use exactly the same approach to protect them. It's likely you stumbled upon this pets versus cattle meme before, multiple times maybe, where one actually shifts from treating machines as snowflakes with a very tailored approach to them, and instead starts dealing with machines more like cattle in a more uniform, standardized, and somewhat detached manner. I think that the same comparison can be drawn when comparing securing end-user machines versus securing servers for actually a number of reasons. One of those reasons is scale and context. This map actually provides a rough outline of the geographical distribution of Cloudflare points of presence around the world. Each of these points of presence have a significant number of machines that need to be maintained and secured. So it wouldn't really be practical or even affordable to have a very customized process to keep each and every of those machines in a secure state. The context in which those machines are being maintained also differs, since when we think about an end user machine, we typically have a person sitting behind them we can rely on to do whatever maintenance operations need to be done. In a server deployment, machines are generally being operated from afar, which just complicates things even further, as any operation is generally being done over the network those machines are powering themselves. So the second reason I'm going to touch upon is threat model. As much as we would like to believe that our own laptops and desktops are likely targets of highly sophisticated attacks that make use of zero-day vulnerabilities, that's generally not the case for many of us, or for a large majority of us. However, when you're providing services and have a modest to significant amount of hardware on your fleet, software and data flowing through your systems, your infrastructure naturally becomes a more attractive target to attacks. And also, the types of attacks that would not be reasonable to be included within the threat model for your own machine are actually central attack types that need to be defended against in a server deployment. The high-level differences seem relatively straightforward to understand, but what does it actually mean in practice? We are going to take a closer look at two specific areas. The first one is going to be boot and runtime security, and the second one is data encryption at rest. And we will try to illustrate with some examples of what we are doing at Cloudflare today to tackle these problems. So I don't know if you ever thought about or explored what happens when you press the power button on your computer until your operating system is fully booted and your system is working. From a high level perspective, when the system is powered on, you have a specific chip on your motherboard, which is called the platform controller hub, that powers on and prepares the CPU to start executing, and initializes as well some of the other hardware subsystems in preparation for the boot firmware to be loaded. When that is done, BIOS or UEFI firmware is loaded and the CPU starts executing it. If you have an older machine, you may still be using BIOS, but that's becoming less and less common with more modern machines using UEFI as their firmware. In the case of UEFI, it will itself run a long boot process with a big number of steps, and at some point it's going to read the boot configuration to select the order in which it's going to attempt to boot from the available devices. At some point, it's going to find the correct boot target and will load a bootloader. The bootloader is responsible for preparing the system further to boot the operating system kernel. Grub is one of the prime examples of bootloaders out there, even though different operating systems have different approaches to this phase. So, for example, if you take Windows, it has a bootloader of its own that is integrated into the operating system. Once the bootloader has completed execution, execution is transferred to the operating system kernel, which initializes all its own subsystems and prepares the user space applications to finally start. So Now, if we look at this from a security perspective, there are plenty of things that can go wrong, since we have so many points where trust is transitioned over between components. One of the security mechanisms available in UEFI firmware, and that's being increasingly adopted today, is Secure Boot. The whole idea around Secure Boot is to make sure the boot chain, starting from the bootloader, has been cryptographically validated to have been signed by a provider you're choosing to trust. And that provider is, in most cases, your operating system vendor or distributor. Among other things, it's protecting you from a compromised operating system update procedure where an attacker is able to tamper with your operating system image, or from an attack that tries to tamper with your system early in the boot cycle. In some cases, you have the operating system with abilities to validate the applications that it's going to load afterwards, but that's tendentially a less uniform space, even within the same platform. What I mean by this is that on most operating systems, you still have a way to load a potentially malicious application, because you're generally a power user on your own machine. Exception maybe for mobile operating systems, which have historically been fairly locked down from that point of view. So if you look closely enough, you probably understand that UEFI firmware itself is being loaded from somewhere, and that because we are hooking trust at the firmware itself, there is no authentication or integrity check being done to this firmware. So if you manage to compromise UEFI firmware, the whole secure boot chain collapses, as the attacker could just remove all validations being done to the bootloader and the OS kernel afterwards. However, carrying an attack like that would require physical access to the machine, and that's generally left outside of the threat model for end-user machines. So protecting against that type of attack hasn't been really common in some platforms out there. If we move to servers, the boot process is largely similar to the one we see on end-user machines, with some tweaks. This diagram is actually a fairly accurate depiction of the boot process we currently use at Cloudflare. The first difference may be that since there isn't usually a person sitting by the server that can just press the power button to power it up, servers are initiated or started through remote management interfaces. The boot process is then started by what is called the baseboard management controller, which you can basically look at it as another computer living inside of the server that is used solely for management purposes. Power management is just one example of the management functions that exist on those platforms. Beyond that, if our infrastructure in Cloudflare's case runs mostly on a stateless operating system, which basically means that the operating system is being downloaded and executed each time the server is rebooted. This is not only a nice way to keep our server fleet always up to date, but it's also a good way to ensure the software stack being ran is uniform across the fleet. IPXE, which is a pre-boot execution environment, has nice scripting abilities and allow us to do just these in a secure fashion. Secure boot is also an important piece in securing the boot process, and more so if one considers that the frequency and the number of updates that are being added to the system is way higher than in an end user machine, since that can pretty much happen on every single reboot. However, just in the end user machine case, the secure boot is exposed to an UEFI compromise. This threat is even aggravated if you consider that management functions that previously required physical access to the system now can be done remotely through the network using the baseboard management controller. Among those management functions is the installation of firmware updates. If that management function is not properly secure, can exactly lead to the type of attack we've been describing. So there is a very nice blog post by some of my colleagues that goes in depth into this problem and defines what we are attempting to do to solve it. That I would really recommend you to take a look at if you're interested in this topic. But from a high-level perspective, you can think about it as extending the trust chain all the way to the CPU hardware. In this case, because trusted is rooted at the CPU before firmware is even loaded, you can be sure that only legitimate firmware is going to be running on your machine. Since this chain is maintained until the UEFI secure boot process kicks in, it can be ensured that an end-to-end trust chain is maintained throughout the boot process. In our case, this feature makes use of CPU hardware features present on AMD CPUs that we are currently using on our infrastructure. The platform secure boot feature, which is what it's called, is enabled by writing into a region of one-time programmable fuses on the CPU die with the serial number for a certificate that is then going to be used to sign the firmware images that should be accepted. This procedure is normally done at provisioning time, which is a period where the machine is less exposed from a security perspective. So we can be assured that it wasn't tampered with. Then, when the CPU is loading firmware, the platform security processor, which is a security coprocessor built into the CPU, validates that firmware it's trying to load has been signed with the key the CPU has been configured to accept. I think one of the advantages of this feature from a security perspective is that once it's enabled, it can't really be disabled because these OTP fuses cannot be erased. This makes it impossible for either an attacker or a system administrator to disable this feature, and so we keep the system secure regardless. But the boot process is not really the only place where lower level hardware attacks become more important from a server security perspective. As we already mentioned before, the distance between the operators and the machines, and also the value of the data being handled by servers, makes them a more likely target for sophisticated hardware attacks. Cloudflare works pretty hard to protect the physical locations where our servers are operated on. However, we believe that alone shouldn't stop us from trying to protect from worst case scenario type of attacks. One example would be if someone would be able to steal a server from one of our facilities and take with it a large quantity of potentially sensitive data. While we make extensive use of data encryption at rest, which we'll actually be talking about a bit as well, that data is still manipulated in clear when it's being handled by the CPU and stored in main memory. This has actually been a fundamental feature of computer architectures probably since computers exist. And there were not many tools available to secure this aspect. When the CPU needs to access a memory page, it checks if that page is mapped in one of the memory page tables and reads or writes the memory page from main memory if required. As you can see, there is no encryption process involved in this exchange. So this communication is effectively done in clear. Why is this a problem since it's all happening in the same computer? You may very well ask. Well, firstly, we've seen DRAM snooping and even memory freezing attacks being described and being made practical in the research communities. And secondly, there are industry trends pointing towards non-volatile memory, where memory would still contain data even after the server is powered off, or even if memory was cut power. These reasons, coupled with the threat outline described before, justify taking a deeper look into how to protect memory from these types of attacks. Again, if you want to take a more in-depth look at this problem and how we are solving it, you can just take a look at the blog post that is referenced on this slide. It's really, in my opinion, a rather elegant solution to a fairly complicated problem. But the solution, just to give an overview once more, relies on security features being shipped into modern CPUs. In this case, AMD provides the ability to transparently encrypt and decrypt memory pages before they are written to and read from. The encryption and decryption process is entirely managed by the platform security processor, so it's generally transparent to the operating system, making it possible to enable this feature or on otherwise standard hardware. This feature can either be enabled at the system level. In this case, it's called transparent memory encryption, or on a memory page basis, giving you either broad coverage or granular control, depending on the use case you have. I must really confess that I didn't believe this was possible before I saw it implemented in our infrastructure, but more importantly, that it would be performant enough to be used on a production system, given that memory bandwidth is usually fairly high, and you have an added cost to encrypting and decrypting each memory page on every access to main memory. However, after we actually measured it, and if you look at the charts on this slide, the benchmarks we've done show that actually the performance impact is fairly minimal, which makes it a practical defense to deploy across an entire server fleet. All right, but enough with talking about boot and runtime security for now. Let's look at a related but slightly different topic, which is data encryption at rest. Given the nature of data stored on computers in general, either temporarily or in a more permanent way, it's really important to make sure that data is properly encrypted and the encryption keys are properly managed. I'm overly emphasizing the Cloudflare blog, but as you probably can tell by now, I'm a huge fan. And we've blogged as well before about Cloudflare's approach to disk encryption, including a very nice explainer of how it works under the hood in the Linux kernel. I'd really recommend you to take a look at the blog post that's linked here. And it was even interesting that as a result of this effort, Cloudflare ended up contributing changes to the upstream Linux kernel source to make sure the performance profile of the disk encryption subsystem matched our requirements, which was pretty neat. So There is one aspect of encryption at rest that still makes sense to discuss in further detail, and that's related with bootstrapping trust. Let's again draw on the comparison between end user machines and servers to better understand that problem. When disk encryption is enabled on an end user machine, it typically relies on some form of user authentication, as Alec was describing in great detail before. And that authentication is used to enhance the key generation process. What this means is that trust for the disk encryption process is being bootstrapped from the fact we have a user present or a user authenticating, and that authentication has been successfully completed. And that determines that data should be unlocked and the user should be able to access it. However, if we try to map that into servers, the scenario is fairly different. So as we've seen, system administrators are typically far from the machines they are managing. And in any case, it wouldn't really be practical to just require someone to type a password to each time a server needs to be booted. So there are a couple of things that we can do. One example would be to rely on a remote key repository containing the encryption keys for all servers in your fleet. Well, beyond that, not being just a desirable solution, really, as it would be just a single point of failure and a very desirable attack target, it wouldn't still help much on making sure the correct server and only the correct server is receiving the correct encryption keys. Another idea potentially we could think about would be to store the encryption key on the server in some storage that is not the one we are encrypting. However, with this, we would end up in one of two scenarios. That key would either be stored in plain text, which is again undesirable and ultimately insecure, or we would encrypt that key with some other key that would also have to be stored somewhere, which, if I'm seeing it correctly, is kind of a catch-22 situation. So this is a seemingly impossible situation to securely address on server environments. Well, not quite. Enter the Trusted Platform module, which is also commonly known as TPMs. TPMs exist nowadays in the vast majority of servers, and it's increasingly common for you to find them on end-user devices. Despite being a fairly small chip, it actually packs a lot of punch and can be an instrumental tool to support a variety of workflows and applications. Among the set of features provided by TPMs, there are three that can be leveraged to support disk encryption on servers. And those features are remote attestation, TPM encrypted storage, and secret sealing. I'm just going to be briefly talking about the three of them. And in the remote attestation case, it is a process supported on the TPM to prove two things to a remote party. First, it proves the system state, meaning that the firmware and operating system and software combination loaded on the system matches a given set of cryptographic hashes, and that proves that the state is the one running on the machine. And secondly, it is used to prove that the identity of the machine itself. The first part is achieved by a tight integration with the firmware layer and the TPM, and with the other layers on the boot chain, where each level measures the components of the next level into the TPM before handing over execution to them. The second part is made possible by the existence of what's called an endorsement key, which is essentially a cryptographic key burned into the TPM when it's being manufactured, which can be used to prove that a given operation was executed by the TPM installed on a given machine. Think of it like a client certificate whose private key never leaves the TPM. So combining these things, the remote attestation procedure allows a server to authenticate itself with a remote server and, for example, use that authentication procedure to retrieve the disk encryption key that is stored remotely. The other two features are related but slightly different in how they can be leveraged for the purposes of this process. Encrypted storage allows you to encrypt some data with a key that never leaves TPM. This can, for example, be used to encrypt the header of a storage volume and decrypt it before the volume can be unlocked. This would make sure that the volume can only be unlocked on the machine containing the TPM that was used to encrypt it. On the other hand, secret sealing goes a bit further than encrypted storage, and in this case, it's used to encrypt some data, for example, the disk encryption key, with another key that's resident on the TPM, but specifying as well that the system must be in a specific state for the key to be allowed to be decrypted. This system state definition would be like the one that is used on the remote attestation procedure. This would allow to ensure that the key can only be unlocked on the machine it was initially logged to, but also that the machine has been authenticated without having to rely on any external third party for that. There is a lot more to be said about TPMs and how they can be used in practice in either of these contexts. So just stay tuned as we will be talking more about it in the future. So in conclusion, there are fairly important differences between securing end-user machines and servers. And while many of the problems are common, solutions need to be adapted for the different context. Hardware security features are becoming increasingly important to secure servers throughout their life cycle. And finally, TPMs can be a great tool to support server authentication and secret management at a relatively low cost. So that's it for me today. Thank you very much for your time. And now I'm open to answer any questions you may still have.
Thank you so much, Jean, for your presentation. Everyone that is joining, our audience, if you have any questions, now is the time to do them. While we see if we have any questions, I have a question for you. Before you said that you started working at Cloudflare in June last year, correct?
Yep.
So you did your onboarding remotely.
That's true.
What do you think is the main advantage and the biggest challenge of working remotely and having your onboarding remotely?
So I think it becomes a different experience onboarding into a company when everyone is working remotely, but it's still a very positive one anyway. So everyone is more aware of the special circumstances we are all going through, and everyone is super conscious and super welcoming and super receptive about that. And it also makes it easier for you to prepare yourself mentally to work on a geographically distributed team. So if you're not sitting with your team at an office the whole day and just interacting in person, you have to develop methods and techniques to collaborate with the people that are on the same geo you are, but also with everyone else across the globe. So it definitely helps, and it's a great way of developing those skills and learning more about that. On on the onboarding side, it was also an interesting experience to be able to learn about so many different aspects of the company in a relatively short amount of time from people also all around the globe. So it was a great experience and a great way to get started on my Cloudflare journey.
Nice. Thank you so much for your answer, João. We have here a question. Okay. The AMD memory encryption uses a single CPU hard-coded key, or is it rotated in somehow? If hard-coded, how vulnerable it becomes when, let's say, quantum computers enter chat?
Yeah, that's definitely a great question. So no, it's not a hard-coded key. It's a key that is generated on every boot, and it's even there is a degree of indirection on which key can be used for which memory pages. So it's definitely not the hard-coded one. And yeah, it's a valid concern to have if it were, but it's not. So you're fine from that perspective.
Okay, perfect. So
I hope it answered.
Yeah, I hope you answered the question. If you still have any doubts, let us know. For now, we don't have any questions, and we are right on time. So maybe Alec want to join us here in the screen just to say goodbye to everyone. Once again, Alec and John, thank you so much for your presentations, and to everyone that joined us today and participated in the session with questions and in the chat. Cloudflare is currently recruiting not only for security. So if you want to know more about the jobs, you can always check them in Landing.Jobs. And I hope to see you all tomorrow on day 3 of Cloudflare Week. Tomorrow we will have the product day with Mark and Malavika talking about building privacy first web analytics and threat intelligence at Cloudflare. Sorry. So I hope to see you all tomorrow, and thank you once again. Enjoy your day. Thank you, everyone.
Thanks, everyone. Bye-bye.
Bye.